Hey everyone, and welcome back to the Linkfitties Deep Dive Show. Today, we're diving deep into some seriously cool AI tech that's changing how we think about animation. Imagine being able to create a lifelike animated video of anyone, even yourself, using just a single image and an audio clip. That's the promise of OmniHuman, a new AI model that's pushing the boundaries of what's possible in animation. It's not just about faces or simple gestures. OmniHuman aims to capture all human movement, from subtle facial expressions to complex interactions with objects. Now, this isn't just some pie-in-the-sky concept. It's based on a solid research paper titled OmniHuman1, Rethinking the Scaling Up of One Stage-Conditioned Human Animation Models. It's a mouthful, I know, but what it boils down to is this: OmniHuman is a powerful AI model trained on a huge dataset of human motion data, using something called diffusion transformers to learn the intricate relationships between images, audio, and poses. Okay. So, diffusion transformers. That sounds pretty complex, right? Let's break it down. Think of it like this. Imagine you have a blurry photo, and an AI gradually sharpens it by adding details. That's similar to how a diffusion transformer works, but instead of a photo, it's building a video, frame by frame. It starts with a noisy image, and then refines it step by step based on the input data. This could be audio, pose information, or even a text description. So, it's like the AI is learning a dance routine where each piece of data, whether audio, pose, or image, is a step in that routine. But what makes OmniHuman stand out from previous models? Well, it's the Omni conditions training approach. This means they're not limiting the training data to just one type of input. They're using a mix of text descriptions, audio recordings, and pose information, all combined with video data. Why is that such a big deal? Well, traditional models often rely on very specific data that's been carefully filtered and cleaned. For example, an audio-driven model might only use data where the lip movements perfectly match the audio. This approach limits the amount of data that you can use for training. OmniHuman, on the other hand, embraces the messiness of real-world data by mixing different types of input. This allows it to learn from a much larger and more diverse dataset. This ultimately results in more natural and realistic animations. Think of it like teaching someone to cook by having them watch cooking shows, read recipes, and get hands-on experience in the kitchen all at the same time. They'll learn a wider range of techniques and be able to adapt to different situations much better. And the results are pretty impressive. Omni consistently outperforms other state-of-the-art models on various technical measures. The animations are smoother, the timing is better, and there's a level of detail that was previously unattainable. Now, what can OmniHuman actually animate? Researchers have used it to animate everything from photorealistic humans to stylized anime characters, and even inanimate objects. And it's not just limited to simple movements. The model can generate complex actions like dancing, playing musical instruments, and interacting with objects in a scene. Yes, you heard that right. They're animating inanimate objects. Not quite making a coffee cup do a backflip, but they have examples of a teddy bear waving its paw and a chair reacting to someone sitting down. It's fascinating to see how the AI imbues these objects with a sense of life and personality. So, how does OmniHuman achieve these impressive results? Well, it builds upon a pre-trained AI model called Seaweed, which is already good at generating videos from text and image prompts. Seaweed uses a diffusion transformer, or DIT architecture, which is well suited for this type of task. The researchers supercharged this existing model with their unique training approach. It's like giving a talented artist a wider range of tools and inspiration to work with. Let's say you give OmniHuman a photo and an audio clip, for example. How does it use that information to generate the animation? Well, it's a multi-step process. First, they convert the audio into a format the DIT model can understand using something called wave-to-vec. This involves extracting features from the sound and compressing them, so they align with the internal workings of the DIT. It's essentially translating sounds into a language that the AI can understand. Then, the reference image is integrated into the process, ensuring that the animation stays true to the appearance of the person or object being animated. OmniHuman uses the original DIT backbone to encode the reference image, compressing it into a manageable representation using a variational autoencoder, or VAE. Another acronym to add to the collection. Both the image and audio information, now in a tokenized format, are fed into the DIT model. This allows the model to learn how the sounds relate to specific movements, and how those movements should be reflected in the animation, while also ensuring that the visual appearance stays consistent with the reference image. They also have to take steps to make sure the model understands which tokens refer to the image and which refer to the video, which they do by manipulating something called the 3D rotational position embeddings, or ROPE. Okay, that's getting pretty deep into the technical details. But the point is they've come up with clever solutions to integrate different information and make it work seamlessly. That's what allows OmniHuman to generate such realistic and expressive animations. It's not just mimicking movements, it's learning the underlying relationships between sound, visuals, and motion. And it's really remarkable how they've managed to train the model on such a massive and diverse dataset. Now, let's delve a bit more into that conditions training. It's a radical departure from traditional methods. Instead of focusing on very specific tasks and carefully curating data to fit those tasks, OmniHuman embraces the chaos of real-world data. It's saying, hey, even if this data isn't perfect for this one specific task, it might still be valuable for learning something else. OmniHuman uses all the data that would normally be left on the cutting room floor. They have two key principles for making this work. First, they recognize that tasks requiring strong conditions, like precise pose data, can benefit from weaker conditions, like textual descriptions. Even if you can't teach the AI to perfectly mimic a ballet dancer's every move, you can still teach it about general body movement from a simple text description like clip or twirl. Second, they adjust the training ratio based on the strength of the condition. Stronger conditions, like pose data, tend to dominate the learning process, so they reduce the ratio for these stronger conditions to prevent them from overshadowing the weaker ones. It's like making sure everyone in a group project gets a chance to contribute, even the quieter members. It's about finding that perfect balance where all the different types of data can contribute to the learning process. This approach allows them to scale up the training data significantly without sacrificing performance. Let's talk about how OmniHuman is driven by different modalities like audio or pose data. Imagine creating an animation of someone dancing. You could provide the model with a photo of that person and a music track. OmniHuman would analyze the music, identify the rhythm and beat, and generate dance moves that synchronize with the music. You could also control the animation using pose data. You could create a sequence of poses like a storyboard, and OmniHuman would use that information to generate smooth movements between those poses. You could even combine modalities, using an audio track for timing and rhythm, and then using pose data to fine-tune specific movements and gestures. Now, creating something this complex is bound to have its challenges. One of the biggest in video generation is maintaining consistency over time. It's easy to generate individual frames that look realistic, but stitching them together into a seamless video where movements flow naturally and identities remain consistent is a whole different ball game. They had to come up with innovative solutions. So, to address this, the researchers feed the last few frames of the previous segment into the model when generating the next segment. This provides a short-term memory for the AI, allowing it to remember what happened before and maintain that consistency as it generates new frames. Training a model like OmniHuman requires a massive amount of computing power and data, and that's another hurdle that needs to be overcome. Fortunately, the researchers have made efforts to address this issue. They designed the model with efficiency in mind, employing techniques to reduce the computational load without sacrificing performance. They recognize that to reach its full potential, this technology needs to be accessible to a wider audience. And as hardware continues to improve and cloud computing becomes more readily available, we can expect these models to become even more accessible in the future. As with any powerful tool, we need to consider the potential downsides, like the potential for misuse in creating deep fakes or spreading misinformation. It's a pretty scary thought to consider that this technology could be used to create convincing fake videos that could deceive or manipulate people. But there are efforts underway to develop tools and techniques for detecting deep fakes. It's also about promoting ethical guidelines and fostering a culture of responsible use, making sure this technology is used for good and not for harm. But before we get too far into the potential downsides, let's circle back to the research paper. How did they actually test its performance? They conducted a series of rigorous experiments to evaluate OmniHuman's capabilities and compared it to existing state-of-the-art models. They used industry-standard quantitative metrics like FED, FVD, and Sync-C to measure things like visual quality, motion smoothness, and lip sync accuracy. And the results? OmniHuman exceeded expectations, consistently outperforming other models across a variety of tasks. Whether generating animations from audio, pose data, or a combination of both, it excelled in creating realistic movements, handling complex scenes with multiple characters, and even animating stylized content like anime. And this is just the first iteration of OmniHuman. The research team is already working on future developments and improvements, such as refining gesture generation, particularly the finer movements of the hands, and making the animation even more controllable, giving users more precise control over facial expressions and body language. The real-world applications of this technology are truly mind-boggling. Imagine creating lifelike avatars for virtual reality, or generating digital doubles for actors in films, or even developing virtual assistants that look and move like real people. You could even use this technology to create interactive educational experiences, historical reenactments, or therapeutic tools. This research is really exciting because we're witnessing the birth of a technology that has the potential to reshape our world in profound ways. As we move forward, we must approach this technology with both enthusiasm and caution, being mindful of the potential risks while also embracing the incredible opportunities it presents. It's a reminder that technology is never neutral, but a reflection of our values and choices. As we continue to explore this uncharted territory, it's essential that we have these conversations, think critically about the implications of AI, and work together to shape a future where technology serves humanity. And that's all the time we have for today. Thanks for joining me on this deep dive into the world of OmniHuman. It's been a fascinating journey. I can't wait to see what the future holds for this groundbreaking technology.